Even though stars lie at vast distances, the basic physics of stars has been understood for a long time. Much of it was worked out by Arthur Eddington over a century ago. And this was despite the fact that nobody really understood the composition of stars, and the energy source within stars was still a complete mystery. We now know that protostars, which are essentially just huge balls of gas, contract under their own gravity until the temperature at their centre reaches about 10 million degrees, at which point nuclear fusion reactions kick in and the protostar becomes a star. The thermal energy generated by the fusion reactions balances the tendency for the star to contract under gravity, and the star will continue shining for millions, billions or even trillions of years depending on the mass of the star, until eventually its nuclear fuel is depleted. For historical reasons, stars that are fusing hydrogen into helium in their cores are known as main sequence stars. This phase takes up the majority of the life cycle of a star. So most stars are main sequence stars. But this is just a name. They're not actually following a sequence in the way that the name might suggest. The most important feature of a star is its mass, as this determines most of the other properties of the star. Increasing the mass of a star increases the gravitational pressure, and this produces higher temperatures at the centre of the star. And nuclear fusion reactions are very sensitive to temperatures, so increasing the temperature increases the amount of energy generated, and this increases the luminosity of the star. And this has dramatic consequences on the evolution of the star. The Sun is in the middle of the possible mass range for stars. The Sun formed about 4.6 billion years ago, and the hydrogen fuel for the fusion reactions in its core won't run out for another 5 billion years or so. Most of the stars that we see with the naked eye are brighter than the Sun. This is because although brighter stars are rare, we can see them from much greater distances because they are so luminous. But the vast majority of the stars in the galaxy are red dwarfs, which are much less massive than the Sun. Roughly speaking, a star with about 10 times the mass of the Sun will shine about 3,000 times as bright. So even though it has much more nuclear fuel, the fuel is used up in about 1/300th of the time, which is about 30 million years. And this is one reason why really bright stars are so rare. They use up their nuclear fuel so quickly that they do not hang around very long by cosmic standards. dwarf stars are less massive than the Sun, but their composition is essentially the same as that of the Sun, and the fusion reactions at their core are essentially the same as those within the Sun. But because they are less massive, the temperature in their core is lower than in the centre of the Sun, so the fusion reactions happen much more slowly, and this means they are much less luminous. A red dwarf with about 1/10 of the mass of the Sun shines feebly with just about 3,000th of the luminosity of the Sun, and its nuclear fuel will last for about 300 times as long as the Sun, which is about 3 trillion years. And this is much longer than the current age of the universe. So all but the very closest red dwarfs are far too feeble to be seen with the naked eye. When stars run out of their hydrogen nuclear fuel, it can have dramatic consequences. And we will take a look at these in a future video. For now, we'll look at examples of stars of different masses that we can see in the night sky. The brightest star in the night sky is Sirius, which is one of our closest stellar neighbours at a distance of 8.6 light years. Sirius is a great sight in the northern hemisphere winter night sky. Sirius is the dog star, the companion of Orion the hunter, and Orion's belt of 3 stars points downwards towards Sirius, as we can see in this image. Sirius has a mass that's about twice the mass of the Sun and shines about 25 times as bright as the Sun. In total, its hydrogen nuclear fuel will last for about 1.5 billion years. Alkaid is an example of an even more massive star. This is the star at the end of the tail of the Great Bear, or alternatively, the end of the handle of the plough, or in North America, the Big Dipper. Alkaid is estimated to be about 10 million years old and to have a mass of about 6 times the mass of the Sun. So it's a very luminous star, shining with about 600 times the luminosity of the Sun. And the only reason it isn't as prominent in the night sky as a star like Sirius is because it's much further away. It's over 10 times as far away as Sirius, at a distance of 101 light years. The Orion Nebula that we can see in this image is a star-forming region at a distance of about 1500 light years, and it contains many bright young stars that are estimated to be a couple of million years old. One famous group of stars within the Orion Nebula is known as the Trapezium, and it consists of 5 or 6 very bright stars, but they can only be seen with a telescope. And these stars are estimated to have about 15 to 30 times the mass of the Sun, and they will continue shining for another 2 million years or so until their hydrogen nuclear fuel runs out. In the next video, we will take a look at the nuclear fusion reactions that take place in the core of the star and how they affect the evolution of the star. Thank you for watching the third of our videos about the life cycle of stars. And please don't forget to click the subscribe button because we'll soon be uploading more adventures from the Cosmic Mystery Tour.